Assalamu alaikum. Today we are going to discuss about lecture number 7, axial load and principle of superimposition. My name is Muhammad Arif Aziz and welcome to the lecture. Before proceeding, we have to have a concept of modulus of elasticity. What is modulus of elasticity? Modulus of elasticity is represented by stress over strain. Here we are going to talk about elastic deformation. What is mean by elastic deformation? Elastic deformation is change in length due to the application of load in the elastic zone. This is cause the change in length. It is a deformation in the elastic region. Now, here we have modulus of elasticity, which is E, and 1 minute. Here we have modulus of elasticity, which is E, this is elasticity. Okay. This is stress and this is strain. We know that what is stress? Stress is load per unit area and strain is change in length, that is change in length or elastic deformation divided by original length. Okay. So here let me erase this one. Here we have put these two terms into this formula. Here we are putting this two term. Here we are putting this two term, stress or strain, in this formula. Okay. So it will be P over A divided by change in length over original length, all that equals to E. So it will be E is equals to P L over A deformation, or elastic deformation will be is equals to PL over A E. So this is a formula for elastic deformation, which is derived by using the modulus of elasticity. Now, deformation of axially loaded member. Constant load and cross-sectional area. So there is a member of length L. So we apply the load on either side P. So when we apply the load, the member will be have some deformation in the direction of tension zone. So when it is in the direction of tension zone, we assume it as positive, and when it is in the direction of compression, we assume it negative. So tension, always remember sign conversion. When we have a deformation positive, it is tension. When we have deformation negative, it is compression. So several different P or A or E. Okay. Suppose when we have a member in which we have different stresses P or force, different areas and different modulus of elasticity. So the elastic deformation is a summation of individual one. So you can say that P1, L1, A1, E1 is equals to plus. Okay. So suppose this is a member. In this member, we have a member A length. We have different points A, B, C, D. So the length of a member LAB, which represented by LAB, the length represented by LBC and LBD. So here we have a tension load of 5 kilonewton, and on the other direction we have a load of 7 kilonewton. Okay, we have 5 kilonewton and 7 kilonewton. So we cut the section first from A to B. We cut the section. So we say that by using the equilibrium equation number 1, summation of forces in the direction of X, in this direction positive, is equals to 0. So this is equilibrium equation number 1. We have 3 equations for equilibrium: summation of forces X, summation of forces Y, and summation of movement, if all remember. Okay, keep remember this one. Of Fy upward positive and anti-clockwise positive. This is our assumptions. Okay. Anyway, so here we have 5 kilonewton in this direction. So we said that, okay, our PAB is acting in this direction. If we apply this in the summation of forces, so we said that we assume this direction positive. So we say that PAB minus 5 is equals to 0. Then PAB will be equal to 5 kilonewton. So this, as per our assumption, we determine the value of PAB 5 kilonewton. Now, in the second part, we cut the section at C. When we cut the section at C, here we have 5 kilonewton load in the tension zone. Here we have at B to C, we have a 8 kilonewton of force. This is also in the direction of tension. Okay. And here we say that, okay, we will calculate this one by using the formula. Same. We assume PBC in the compression. PBC minus plus 8 minus 5. Plus 8 minus 5 will be 3. So PBC will be 3 kilonewton. Okay. Now we cut the section from this direction. Here we say PCD is equals to 7 kilonewton. So in this way, we have different P, and we can draw a figure here. Here initially, suppose this is our zero line. Okay. This is our zero line. Okay. It's not straight, but it is a zero line. 1 minute, let me erase them, then I'll. So here we calculate PAB, PBC, and PCD. So summation of all the loads here, it will be represented by this formula, summation PL over AE. Okay. Now here we have different P. Length AB and A and E are constant. We assume it right now because it is not given. So here we say that P, it is tension. So we assume it positive. 5 kilonewton multiplied by length of AB divided by A into E. Then positive sign of formula. Then we say that minus 3 kilonewton. Why? Because we assume it in the compression zone. Because when we calculate this one, we get the answer negative and we get the value in this direction. Minus 3. Okay, this is compression. The sign conversion, remember that one. Then we have a sign conversion here as well. The convention is negative because it is compression. So minus 7. So 5 minus 3 minus 7 kilonewton. Okay. We can make a diagram here as well. It assume it as a zero line here. Okay. This is a zero line. From here to here, from here to here, A to B, the load will be represented by this area, which is 5 kilonewton. So this is 0, 1, 2, 3, 4, 5. So this is for the length AB. Then length BC, it is in the negative zone because it is negative 3. So this is our representation till 3. Okay. This is a member. And then minus 7. So for the length CD or the member CD, it will be minus 7. Okay. So this is just a representation. Now, varying load and cross-sectional area. Before we have a uniform load, here we have the varying load and cross-section area. Suppose this is a member, we have a point load P1 and P2. This is two different loads on the direction of L. Definitely, when there is no constant load, when there is no uniform load on the both direction, it will create definitely different impact on the body. When they are creating the different impact on the body, it will be P1 tension, P2 tension. It will give you some. We take one strip and then we integrate it. Okay. that strip, in that strip, we say that dx and delta x and delta deformation is for that particular strip. So the formula will be like this. So it will be like this. Okay. So the constant, also the final version of the formula will be for the varying load and cross section area. It will be P x dx divided by ax dx, because this is a variable load and cross section. And then we apply the limit from 0 to L, because initially the length will be 0 and it will apply till the length L. So this is a limit application and integration. According to the principle of superposition, states that the resultant stress or displacement at a point of member subjected to different load component can be determined by the following things. Number one, first finding the stresses or displacement caused by each load component acting separately on the member. Then the resultant, that is total stress or displacement, is then determined by algebraic adding the contributed cost by the each of the components. Suppose this is a member D, due to which we have and there is a point load in the corner. Okay, due to which there is a deflection. So they said that there is a member we convert into D1 and D2. So till here to here we have a P1 and then we have a P2. Then this is a different like two different beams and they are equal to this one. So start with the problem number one. There is a copper shaft is subjected to axial load as shown. Determine the displacement of end A with respect to end D if the diameter of each segment are diameter of AB is 0.75 inch, diameter of BC is 1 inch, and diameter of CD is 0.5. And assume ECU, modulus of elasticity of copper, is equals to 18 into 10 raised to the power 3 KSI. Okay. So here we have a figure in which we have a member AB, BC, and CD. So there is a applied load on a different segments, 8 kip in the direction, in the compression direction for member A. There is a load for member B, C, and D. So the values are 8, 5, 2, and 6 kips. So this is a free body diagram of a member in which we have member AB, BC, and CD. The length of AB is 80, BC is 150, and CD is 100. So we have different loads. Here we have 8 kip, we have 5 kip, we have 2 kip here, and here we have a 6 kip. I didn't write the units because it's difficult to write here. But anyway, so now we have to determine the value of PAB, PBC, and PCD. Okay, so for the PAB, we just cut that section here and make it again. So it will be, so this one PAB, okay, and this is 8, and if we assume PAB in this direction, so by using the equation of summation of force in the direction of x is equals to 0, it will be, and we take this direction positive, so minus 8 minus PAB, or PAB is equals to 0. Similarly, for the second figure, we cut the section from here to here, from A to C, we cut the section. When we cut the section will be like this. Yes. and this one, sorry. So it will be here we have 8 kip, then we have 5 kip for both the direction, 5 5, and here we have PBC BC PBC. So using the equation, we say that in this direction positive, in this direction positive, so 8 will be positive minus 5 minus 5 and plus PBC, okay, is equals to 0. Then by solving this equation, PBC will be 2, okay, positive. So our assumption is correct. Now third member, we cut the section from another direction, from this direction. From this direction we cut the section. So it will be, when we cut the section, it will be like this. This is 6 and this is suppose PCD. Okay. So then PCD will be equals to 6 minus PCD, and then PCD is equals to 0. Then PCD is equals to 6. Skip. Okay. So we have determined PCD, PBC, and PAB is equals to 8. Okay. Okay. What is the value of, let me erase all this then, because we have no space. You clear this one? Now we have, what is the formula for the deformation? Elastic deformation. The formula is PL over EA. So the formula for the elastic deformation is sigma A D is equals to summation of PL over AE. Now we have calculated different P, that is PAB. I'm writing it here. PAB is 8. BC PBC was recorded as 2, and PCD was recorded as 6. Okay, all are positive. Now in this formula we have 3 different things. So P1 L1 over A1E, because E is constant, then P2 L2 over A2E plus P3 L3 over A3E. ECU is constant, which is 1800 something. Assume PAB is equals to 18 into 10 to the power 3. Okay, which is 18 into 10 raised to the power 3 KSI. Okay, so this is our constant ECU. So we'll put the value here. But L1 is different, P is different, and A is different. Now we know P, we know L. L is 80 for member AB, for member BC it is 150, and for member CD it is 100. Now we have to determine A. Now if you remember, initially they said that diameter of each member is respectively 0.75 or 100 or something. So what they given, diameter for member AB was 0.75, diameter of member BC was 1, and diameter of member CD was 0.5. Okay, 0.5 mm or inch, I think. Okay, because it is in kips. Okay, now we have different diameters, we have different point loads or different forces, and we have different L, and we know constant E. So we get the values here. How? We put the values 8 into 80 divided by area is pi by 4 d square into E value 18 into 10 raised to the power 3. This is for first one. Then plus sign 2 into 150 divided by pi by 4 1 square into 18 raised to the power 3, and respectively for the third one. Here the direction of PAB is like this, CBC and C is like this. So here we put the negative form value. Okay. Then positive sign. Last one is 6 into 100 is the length of the member divided by pi by 4.5 square and value of E 18 into 10 raised to the power 3. When we solve this, we get the value is 0.111 inch. That is deflection at point A with respect to D. Okay. Problem number 2. In the problem number 2, we have the composite A36 steel bar as shown in figure is made from two segments AB and PD. So there is a segment A, B, B, D. Having a cross-sectional area of AB, the cross-sectional area of AB is 600 millimeter square and ABD is area of BD is 1200 millimeter square. Determine the vertical displacement at end A of the displacement of B relative to C. Okay. We have to determine the vertical displacement at point A relative to B and C. Now, again, we put the section concept. We cut the from here to here, we cut the first section as represent. We determine PAB, PBC, and PCD. Okay. So for the PAB here, you can see we have 75 kilonewton upward. We assume PAB downward. So you can put the summation of okay. Here we have summation of forces in the direction of x equals to 0. This direction, sorry, this is summation of forces in the direction of y. That y is upward is positive. Okay. So we said that 75 is positive minus PAB is equals to 0. Then PAB will be 75. So our assumption is downward is correct. So PAB is 75 kilonewton. Then we cut the section at C here. So here we have cut the section and we assume the value before. I don't know, there is some problem in the internet. Anyway, so now we have back on track. For the PBC, the equation will be like this. Suppose for the PBC, it will be suppose our assumption is PBC downward. So 75 minus 20 minus PBC is equals to 0. Then 75 minus 40, it will be 35 minus PBC is equals to 0. Then PBC will be 35 kilonewton. We take it from here to here or here to here. So this is PBC. Now for PCD, we cannot cut the section from downward because there is no force here. So we assume the section from here and we say that 75. So in this one, the equation will be slightly bigger. Suppose we assume PCD downward. Suppose we assume PCD downward. So when we make this equation here, So we said that 75 upward positive, 20 downward negative, minus 20, minus 20, minus 40, minus 40, minus PCD is equals to 0. Okay. So if we calculate it by the formula, by the calculator, 75 minus 20 minus 20 minus 40 minus 40, it will be minus 45. It will be minus 45 minus PCD. So it will be PCD is equals to minus 45. It means our assumption is wrong. PCD is upward. Okay. So now we calculate PAB, which is downward, PBC downward, and PCD down upward. Okay. Now in this one, we have formula of PL over AE. We know length of each member, area of each member, and more E for each member. Okay. From the inside back cover, there's a in the exam it is given, but modulus of elasticity of steel is 210 into 10 raised to the power 3. It is given in the exam. So we have P, we have L, we have A, and we have E. We just put the values and we got the answer. This is deflection at point A. So there's a positive sign which represents that the bar elongate in the or displays at upward direction. So elongation or deformation in at point B with respect of C will be force at BC, length of BC, area of BC multiplied by modulus of elasticity at B. It's E, not B. So we put the values and we get the answer here. So here B moves away from C since the segment is elongates because it is a positive sign. Start with the problem number 3. The assembly consists of a steel rod CB and an aluminum rod BA. Now this is a composite structure in which we have a steel rod as well as aluminum rod. So we have a steel rod CB and aluminum rod BA, each having a diameter of 12 mm. So the diameter of each of the rod are same. So this is 12 mm as well as this one. If the rod is subjected to the axial loading at A and at the coupling B, determine the displacement of a coupling B and the end A. Here we have a axial load at point A, which is 18 kilonewton, and there is a coupling at point B. We have to determine the axial load at coupling B and at end A. The unstretched length of each segment is shown, or you can say the initial length of each of the member is shown in the figure, which is 3 meter and 2 meter. Neglect the size of connection at B and C and assume that they are rigid. Modulus of elasticity of steel is 200 gigapascal and modulus of elasticity of aluminum is 70 gigapascal. Okay. This is our question number 3. So now we have a member here in which we have 3 points, that is 1 minute. So basically this is a member CBA. B is the coupling point and A is a point where we have the load of 18 kilonewton. So we cut the section at B. So to determine PAB, so for PAB it will be like this. Suppose this is a load of 18 kilonewton. So assume PAB in this direction. So PAB, so summation of forces and direction of X, this word positive equals to 0. So it will be PAB plus 18 is equals to 0. So PAB will be equals to minus 18 kilonewton, which means our assumption is wrong, or our assumption is assumed. We have to assume in this direction. So our sign convention is reverse. So PAB is in this direction. Okay. PAB is in this direction. Anyway, then we calculate actually this is a tension in the tension direction, which is positive. Now we calculate for the member PCB. So for the PCB, suppose we cut the section at C here, and we say that okay, this is here PCB. I'm not going to make the new drawing. So it's PCB. Okay. Now we assume it in the outward direction. So PCB minus 6 plus 18 is equals to 0. So it will be PCB. If we take it from the other side, it will be 12 kilonewton. So PCB is also tension, and it is the magnitude is 12 kilonewton, and the magnitude of PAB is 18 kilonewton positive in the tension direction. Okay, because we assume that compression in the initial, I just assume it to show you that how the sign convention change when we calculate it. Okay, we can assume it in this way as well, but just to show you that we can we assume in this way and how the sign convention change the direction. Anyway, so now we have to determine deflection at point B. Deflection at point B. So the deflection at point B will be PL over AE. Okay. Now at B point, the deflection is due to force of member PCB. So we will assume only PCB, length of CB divided by area of CB, and E, that is modulus of elasticity. Okay. Now here this is a steel bar. Okay, this bar is steel and this bar is aluminium. Okay, now this is for member CB. Okay, this is B. I'm continuously making B. Okay, now what is the value of CB? 12 into 10 raised to the power 3 into length, which is 3 meter, divided by area. Area is given by in terms of diameter. Both the steel bars, both the bars having a diameter of 12 mm. So we are dealing in a millimeter. This is millimeter. We are dealing in a meter because this is 3 meter. So we convert into meter. Okay. So it is pi by 4 d square. D square is 12 mm or 0.012 meter square, and into E. And modulus of elasticity of steel is given 200 into 10 to the power 9 gigapascal. If you remember, it is given, sorry, it is given, E is given for steel 200 gigapascal, which is 200 into raised to 10 to the power 9. And for the aluminum, it is 70 gigapascal. It is given. Initially, I to show you. So it will be 70 into 10 raised to the power 9. Okay. Now we put all the values here. We put all the values here. By solving, we get the 1.59 millimeter. We got the answer in millimeter like this, or in meter it will be 0.00159 meter. Okay. This is deflection at B. Now deflection at A is due to two objects. See, here we have A, we have deflection due to two forces, member force AB and member force BC. So our equation will be summation of PL over AE, and that summation is for PAB LAB divided by AAB plus modulus of elasticity of aluminum plus this one. Hold this formula as it is. How? Like PCB plus multiply by length CB divided by ACB into, okay, this is also into modulus of velocity of steel. So we already calculated, we just put the values here and we get the answer. So by putting the PAB is, what is the value of PAB? We calculate here 18. We put 18 into 10 raised to the power 3 into length of AB is 2 into 2 divided by pi by 4. Sorry, it's cut, but it is pi by 4.012 square multiply by 70 multiply by 9. Okay, gigapascal plus 0.00159 meter. So when you solve this, you get the value which is 0.00614 meter or 6.14 millimeter. That is a deflection at A with respect of B. This is the solution of problem number 3. Problem number 4. In this problem, there is an assembly consists of two A36 steel rods and a rigid bar BD. Each rod has a diameter of 0.75 inch. If the force of 10 kip is applied to the bar as shown, determine the vertical displacement of the load, and modulus of velocity of steel is 29 into 10 raised to the power 3 ksi. Okay. In this problem, you can see here we have one rigid bar which is B and D. Okay, this is a rigid bar which represent by B and D. Okay, this is B and this is D. It is suspended by two wires which is AB and CD, and each has a diameter of both the bar is 0.75 inch. Okay, because we are dealing in inch and feet. If a force of 10 kip is applied of the bar here, this force is applied at a rigid bar at point E. This is a new point E, and the value of applied load is 10 kip. Okay, it is not acting on the center of the bar. You can see that it is 1.25 feet from this point and 0.75 feet for this point. So the total length of member BD is 2 feet. Okay, this is 2 feet. The length of wire BA is 2 feet. The length of wire DC is 2 feet. Okay, remember all these points. So first of all, we have to determine internal forces and in member or in wire AB and CD. Okay, so we have to make a free body diagram first. Suppose FAB upward, FCD upward, and this is a load of 10 kips. Okay, now this is the distance between here, it's 1.25 and this one is 0.75. If you remember, this is member FAB, this is member FCD. Okay, and this is a load of 10 kip at, this is point E, and assume it F. Okay, so load or force at EF is equal to this. So this is point B and this is point C. Okay, now this is a clear picture. We have to take, first of all, we have to determine FAB and FCD. To determine FAB or FCD, we have equation of equilibrium, three equations of equilibrium. Remember, summation of forces in the direction of x equals to 0, summation of forces in the y is equal to 0, and summation of moment at any point is equal to 0. Okay, so here we have to calculate summation of moment at point B first to determine FCD. So summation of moment at point B is equal to 0, anti-clockwise positive. So the equation will be FCD times 2, the total length, minus 10 times 1.25. What is this 10? This load, and 1.25, it is clockwise. So we assume it clockwise, it will be equal to 0. So FCD will be equal to 6.25 K. This is a third moment of equilibrium. Now use second equation of equilibrium, summation of forces in y is equal to 0, upward positive. So we say that 6 FAB upward plus FCD upward minus 10 equals to 0. We know FAB, so we FCD, we know FCD. We put the value of FCD, which is 6.25. So 6.25 minus 10 equals to 3.75. So FAB will be 3.75 K. Okay. So we have the FCD, FAB. Now deflection at point B and deflection or strain at point B and D will be calculated by the following formula. Okay. Now what is the formula for deflection? Deformation, it's equals to PL over AE. Okay. Now for the member AB or at point B, it will be force at AB multiplied by length of AB divided by area of AB into modulus of elasticity of steel. Okay. Now what is the force at AB? We calculated 3.75. 3.75 multiply it skips multiply by length. What is the length here? If you remember, we have a length of AB is 2. So 2, it is in feet. So 2 feet multiplied by 12. It will be in inch. Please remember the unit conversion in exam as well. Now divided by area. So diameter was given 0.75. So pi by 4.75 square multiplied by modulus of elasticity of steel, that is 29 into 10 to the power 3. By solving this, we get the answer of 0.007025 inch. Same likewise at D, we have P L over AE. So we can represent P by force. So we can say that FCD multiplied by length of CD divided by area of CD multiplied by E of steel. Okay. So now here we have a 6.25 multiplied by 3 feet. So it will be 12. This is a conversion from feet to inch. Okay. Divided by pi by 4.75 square multiplied by 29 into 10 power 3. It will give you the deflection is 0.01756 inch. So this is a deflection at point B and C due to application of load. But we have to determine the deflection at point E here. Okay. Here at point E. So now suppose if this is a member, it will deflect. I'll show you in a second figure. I'll make a new figure and then I'll show you how does it look like. So now we have to make a new figure just to understand the concept. I just noted down the value of deflection at B and deflection at D. Now this is our rigid member which is B to D. Okay. Here we have suppose this is deflection at point B, that is delta B or deflection at B from here to here. Okay. At point D, and the value is of this one is 0.07025. Okay. Now the deflection at D will be slightly higher because these two values are different. So this is slightly higher. So it will be somewhere here. So suppose this is B and this is B dash. So it will be automatically, it is D and it is D dash. Okay. So the deflection will be like this at point D dash. Okay. So this is the deflection at point D. Okay. Now, what is the value here is 0.01756. Now we have point E here and we have E dash here. Okay. We have to know this value of deflection due to the application of a load. Okay. That is delta E. Okay. This is we have to calculate. To make it more clear, we can assume it in a one. We can say it's figure number 1, figure number 2. Figure number 1 consists of point B to E. Okay, from point B to E. Which consists of one triangle and one rectangle. This magnitude we know already. Okay, which is deflection at B. Okay, and this is deflection at E. So the deflection at E is in two parts, you can say. One is a square body and one is triangle body. Okay, this is a triangular body or this is a square body. Okay, now deflection at E will be equal to deflection at E will be equal to whole this. So from here to here, what is the value of the deflection? We know that, which is equal to, because this is equal, which is equal to 0.007025. Okay, so 0.007025 plus this part. Okay, but we don't know this part. So how we can determine this part? We can say that what is the area of triangle? Half A B. Okay, just to keep in this mind, what is A and what is B? A will be this distance, which is 1.25, because this is 1.25 and this is 0.75. Okay, so A is 0.7, and what is B? Now this is tricky part. This one is a deflection at B. Okay, a deflection, we have to determine this one. So what is the total deflection here? 0.00725. And what is the total deflection here in this point? Which is 0.01576. So 0.1756 minus this will give you this, which is 0.007025. Okay, so by solving this, you get deflection at E will be 0.01361 inch. Okay, this is deflection at E. Now this is due to the this is because of the deflection of B and D. The E should be deflected as well. But if you remember, there is a load of 10 kip. So we have to determine the deflection due to this load, which is deflection due to load equals to PL over AE. So we have P is 10. Length was given, I'll show you, which is 1 feet, 1 multiplied by 12 in inches. Area of that one is pi by 4 d square, 0.75 square, multiplied by E, 29 into 10 raised to the power 3, which is 0.009366 inch. So that overall deflection at point E is due to this one, this E dash, this delta E, plus delta E with respect of F, which is load. So delta F is equals to delta E plus delta E with respect of F. So it will be 0.01361 plus 0.009366 inch. It will be 0.0230 inch. Okay. So this is the end of the lecture number 7. This is problem number 4. So I hope it is clear. So see you inshallah in the next lecture. Masama.